Glad to be back. So we have a long afternoon, so I better be going. The plan is to go a little bit more into detail on a couple of applications related to voltage stability and angle stability, more precisely on power oscillation monitoring. And I show some examples. I also have a little bit about frequency stability and modeling related to that. And also plan a lecture on modeling, control, and dynamic analysis related to multi-terminal DC grids in the power system. So if we come through all this before midnight, then we can be happy. So this is the content of the first part. First, say something about just visualization of phasor measurements, and I will do that in context with what we have at our university, what we call the Norwegian Smart Grid Laboratory. So I'll explain a little bit about that, and then go into voltage stability monitoring and focus on some different methods that have been applied and some that are implemented. Then about monitoring or detection of power oscillations. And then I have a little bit special application that I think is interesting and I would like to share with you. I don't know how relevant it is. This is related to the mostly the 66 and 132 kV networks sub-transmission that we have in Norway. That is where the transformers are, the neutrals of the transformers are grounded through a so-called Peterson coil. So we say that they coil compensated. I don't know if that's much used in India, but if it is, it's finding where the fault is an issue. So I'll mention it. Have you heard about it? Yes? Okay, good. Okay, a few words about the National Smart Grid Laboratory. That is a recent setup that we have. We have a large space in our basement with laboratory components. And also connected to that is some photovoltaics and charging for electrical vehicles, and a so-called smart house. Smart house meaning a house with some modern applications, basically. And there is adjacent to that is our electrical machine laboratory, where the students do the basic learning on lab exercises on electrical machines. And there's a control center. We are building up sort of something to mimic a control center. And that's where the phasor measurement units are relevant. So just to, the reason why I show you this is that it has to do with what I later show of PMUs. The topology in the laboratory is so that we have a number of what we call AC bus bars, the black lines here. They are what we call the bus bars, AC, and then we have a number of DC bus bars. And all this is connected in some kind of grid, which is flexible, so that we can simulate or emulate a power grid in a way. And to these bus bars, there are some permanent connected machines or drives, so that we can we can simulate power plants, and there are loads, and there are converters, and there is a controllable power supply here on 200 kVA for us to sort of make also a real-time simulation which can be connected to the hardware. Couple of pictures. What we call a Busbar in reality is a cabinet like this when we have the actual Busbar and the breakers and the connectors. The small one there is the DC Busbar. It doesn't have that much. And you have feeders so that we could connect lines and so on. And the sketch is here, right, with the Busbar, breakers, and feeders. So we can connect lines in different configurations. We have a range of power electronic converters so that we can set up experiments with both AC and DC equipment. We have used this to simulate, for example, a 3-terminal DC grid connected to the AC system. We have some generators which is connected to a motor drive so that we can emulate power plants. This is used to emulate a small hydropower plant. And there is a selection of reactors here so that we can simulate weaker or stronger lines. Some equipment here with thyristors so that we could emulate short circuits, sudden short circuits. We have larger machines, or not that much larger in power, but this is an experimental machine with a permanent magnet, multipole. It was a design that was sort of aimed at designing generators for wind turbine, multipole generators. And this is the controllable amplifier. That is a very handy equipment because we can program any kind of voltage source, whether it be a smooth source or a source with a lot of harmonics or with pulsations or whatever can be programmed on this one. Okay, and then as I said, the main point of telling you this is that we are also in parallel working with setting up a sort of a monitoring and control equipment for this, which we would call the sort of the control center. And the idea there is that we have measurements from all these so-called bus bars. We equip these bus bars within the cabinet with a PMU, and they feed into a PDC, a computer that collects the measurements so that we can make application based on that. And just skip this because we talked about it. Basically, what one could have in such a setup, or actually in general, is that centrally you have a PDC, phasor data concentrator, that gets data from the phasor measurement units. In this case, our own from the system. This, of course, needs to have a GPS antenna. And you could also have input from other external PDCs. For example, we communicate with PDC in Stockholm or from other Nordic universities. And then on that you could build visualization tools, you could build applications, you have storage, you have in form of database, of course, and the users would then normally interact with those central visualization tools. And at the moment, what is in the lab is these things. We have PMUs. We have an electrical system. We also have a real-time simulator, the Opal RT, that also can generate, has software to generate PMU formatted signals. So this is integrated and provides phasor measurements just as from the real hardware. And we are working on the applications, right? And show you a little bit about all this work. And as I mentioned, in the smartly grid laboratory, we are interested in measurements. Since we are emulating various networks, we are interested in having PMUs on as many as possible on these nodes and the feeders from these nodes. So that is the objective. And from that, we develop applications. Right? So, so you could think of various applications. Something that just displays the phasors and the frequency. Something that make trend curves for frequency, the voltage phasors. Something that makes trend curves for voltage. The three phase voltages and the angles. And if there is some activities in the lab right now, maybe I can show you. So what I do now first on this one, I open the software that I mentioned yesterday that takes care of the communication with the PDC. Okay, this has a number of features. You have a configuration here from the IP address and the ports that you need to contact in order to get hold of the PMUs. I have already set that, so it's just setting the IP address, right? So you know that. Then I can check which measurements I have. And it seems now that there is actually a voltage on very many of these nodes. If you could see here, you would recognize the codes for the different bus bars in the laboratory. We can select. I wonder if there is some interesting thing is to see if there is some phase difference. Let me select a few of these. So what I do now, I have to I'll take this DQC. I can take DQE. And I can take DQD, CDE. And I select them here. DQE and DQ DQE, take this one, DQD, and the frequency. Okay, and I've selected 3 voltages of the same, hopefully the same phase. We'll see. And I'll look at the voltages. It seems like it's the same voltage. Nothing is, there's no load in loading on the in the lab, so it's not very interesting. So let's go back and look at one voltage. Then let's pick this one. Now I rather pick the 3 phases of that voltage and the frequency. It's a little bit the communication is a little bit slow. So you don't see sort of the very smooth reaction here, but you see the voltages in per unit. Maybe I'll take them up in. I can show them in real volts, because then we can. 400 no. 250 and 210 maybe. So this is I don't know if you see, but this is a 5-minute window. And you see now the 3 phase voltages, magnitudes here, and the angles here. So they are plus minus 120 degrees, so they are fairly symmetrical, both in amplitude and phase angle. You see. So this is live from our laboratory right now, and if one is more interested in frequency. You get that here. The color is not good. I should have chosen another color, I see. But I hope you can see the frequency. And the range here is so that 49.9 hertz is here. 50.9 hertz, 50.1 hertz is here. So we see that the frequency has some slow variations within plus minus 0.05 hertz typically. And you see the frequency meter here. That this is typical for the Nordic power system, that you have these slow oscillations in frequency, which I believe, and many believe, is due to the way the hydro plant governors, they are sort of slow, so they have a natural frequency and sort of a resonance frequency in the range of 1 minute. Now you see the frequency is turning low, so it's almost down to what they are allowed to operate on now. But this varies all the time. And then hopefully within the range of the yellow and the green. When I talked about other external PDCs. We used to have connection to PDCs in Alto and KTH and in Copenhagen as well. But right now I don't have that. I can check if we have something, but I don't think so. We used to have something from Lund, but it's not working right now. So we only have our own voltages now. But at least you see that we are able to monitor, even though I'm here in India, I can monitor our power system back home in real time, even though the communication is a bit slow right now. Okay. Any questions to this? Are you any of you sort of familiar with the LabVIEW programs? Have you used that? If you happen to have that in your laboratory, it's not that difficult to build up such a system. Okay, then I leave this for the moment and go back to the presentation. So, what I wanted to do now is to go a little bit more into the subject of voltage stability and monitoring of that. Oh, wrong direction. So, what are we talking about? Voltage stability. Well, a very simple explanation is with this, let's say, equivalent system where you have a measurement of voltage at some in a transformer station, for example, where you have a load. And if you consider the load as an impedance and the rest of the network as a Thevenin equivalent, okay, so at a certain measurement you can see that you have a voltage and you have an active power feeding the load at a certain point. If you reduce the load impedance, you increase the power. So you move somewhere. Maybe because of the increased power, you get a little lower voltage. And you go on like that. The more you increase the voltage, the more you increase the power, you will have some drop in voltage. And at some times within this, with this simple setup, you reach the maximum power transfer to that load. And it will go on like this. So you can draw this curve, voltage versus power, and you have a point here where you have maximum loadability, if we call it that. It's not necessarily in stable point, but it is at least a maximum loadability. So some formal definitions of voltage instability says that it stems from the attempt of load dynamics to restore power consumption beyond the capability of the combined transmission and generation system. So that means that there must be something in the system here that tries to restore the power consumption in order to have an instability. And that might be many kinds of equipment, power electronics like thermostatic controlled heaters or air conditioner and so things like that. Voltage stability also can be or voltage instability incidents could happen over different time scales, from the very short term due to too high motor loads, for example, or there can be a long-term effect due to recovery of or slow recovery of load when the system has been weakened. So there are examples on that or serious incidents in the network that has been sort of more or less due to a voltage instability or a voltage collapse. Very often there are several phenomena involved, not only voltage, but perhaps combined with power oscillation, it ultimately leads to a collapse. So then one can start to discuss the monitoring or the identification of distance to voltage instability or distance to a voltage or to the maximum power transfer. So we are interested in knowing the margins usually. So again, we could look at the methods that have been proposed in the literature. And the first one you might encounter is something related to this index, that if you know the load impedance and you're able to estimate the network impedance or the impedance of the Thevenin equivalent, the ratio between this is an indicator. This index has to be less than 1 to be on the stable side. And you can also, based on this information and the voltage, you can compute based on simple applying simple Kirchhoff's laws. You could compute the margin that you have until you're this point, if you assume that this is a pure linear circuit, right? So with this assumption that this is linear and that you are able to describe the network by the Thevenin equivalent, and the load is an impedance, then okay, you can find a margin. Now, how do we estimate the Thevenin impedance then in real time? That's the main question then. And And that is not necessarily that simple as it sounds. And the first approach were based on that that one thought it would be quite simple. So by taking successive measurements of voltage and current, and assuming that the network impedance stays somehow constant during the period of successive measurements, one could set up just set up a model that for the current and voltage in this circuit, simply E equals V plus J R, or what is it called? CH. And you have that at a time instant. I like and you see that, okay, you measure this, you measure this, and you might assume that the internal voltage remain constant, or you may not if you have several measurements. You can solve for R and X, assuming that they remain constant. So the more measurements, the better you should be able to get a good estimate of the impedance, right? So that could be a least square solution to that. The problem with this is that it really doesn't work. That's the only problem. And there are many reasons for that. I guess the main reason is that the network is never linear. So you get strange results, which is not really usable. For example, what you get, you are no guarantee, for example, that the resistance is positive, which it must be. It would be totally not logical if the resistance would be negative. So there has been some improvement to this one. And one of the improvements was by Glauco Taranto and his colleagues. That made an improvement to the algorithm to provide a solution by an iterative scheme, so that at least the resistance, it was ensured that the resistance would be positive, and it gave some better results. But still there are some weaknesses with the method, and it can be shown that it doesn't guarantee that this converge to the exact margin or the exact point when you have a collapse either. So we have been working with other methods, and the one that seems to be most promising is here referred to the SZ method, and I shall explain that. The concept of this is that you utilize, you compute a sensitivity, and you can start with the same kind of model framework again. You have a whatever network, and you have a demand somewhere that you monitor. So again, you monitor the voltage and the current to the weak part of the network that are exposed to voltage stability problems. Now, what you can do here with the voltage and current measurement is that you can compute the apparent power, for example. Take the magnitude of that. You can compare the load impedance by taking divide the voltage and the current. You get the load impedance. You take the magnitude of that. And then, okay, if the demand is growing, if you have the demand is growing, then you would expect that the apparent impedance is going down. And also logically, when the demand is increasing, the apparent power delivered to the load would increase. Okay, so if you take the sensitivity then of apparent power to load impedance, that will be negative. On the other hand, if so basically when you have a negative sensitivity, you are on the top of the curve. In contrary, if you have a higher demand and the impedance is dropping, while also the apparent power is going down when your demand is increasing, then of course you have a positive sensitivity. And that is a very good indicator that you are beyond the limit somewhere. So this can be used as an indicator itself. And then you have a sensitivity that is basically negative. If it comes to 0 and become positive, then you most probably have passed the maximum loadability limit. So that can be used as an indicator itself, this sensitivity. And if you do some math on that, given using the Kirchhoff's laws, this is described in a paper, at least to be published very soon, and it's described in a PhD. So that should be available from us. You can express the sensitivity as a function of the internal voltage, Thevenin impedance, load impedance, and the power factor. Now, what you don't know here, of course, the unknown from the start. This is measured. This is measured. So the unknown is the internal voltage and the Thevenin impedance. Now again, you can do some modification on this equation to eliminate the internal voltage. And if you call this sensitivity for C, isn't that? So then you can, then you actually have a possibility to solve for the Thevenin impedance. But let's take a look at how this looks if you And this is again difficult for you to see, but this is the magnitude of the load impedance. And this is the sensitivity factor, this. So it's this factor versus the load impedance. And if you draw this this function with at different levels of the Thevenin impedance, and this is also then totally impossible for you to see, but these are the lines with the constant Thevenin impedance. This is the lowest, so this is the strongest connection, and this is a little bit higher impedance. So weaker grid. I'm sorry that this is. I think I have a better picture later, or I should enlarge it. But anyway, if the load is low, load impedance is high, so we might be here. When the load is increasing and the network is strong, it will follow a trajectory like this. That's the point with this indicator. And okay, here it's still safe. You have a good margin here, but when it comes down here, it starts to become critical. And when it passes 0, then you are in trouble, right? So this way here depends on the strength of the network, and the more critical if you follow this here. So what you can do with this further on is that you can eliminate the voltage, and we define this sensitivity with this Greek letter here that I don't remember the name of. Xi, I think. Then you can express this equation with Thevenin impedance being the unknown. And then you have a second order function on that. The angle here, cosine of theta, you can estimate, you can make very good guesses of that, because it's actually the x over r ratio. So this is your theta, and it's very much depend on the type of line you have. So if you have high voltage transmission line, this will be closer to 90 degrees than if it was a low voltage line. So the sensitivity of the error you do here is not that big, and then you can have a good estimate of the Thevenin impedance by solving this equation. So that is why we say that this sensitivity also can be used as a validating tool for the Thevenin impedance or the strength of the voltage. So we have different results, simulation showing that the difference between different methods, load impedance here, Thevenin impedance from the CT method, Thevenin impedance from a pure power flow computation, taking into account the impedance of the lines, then it's constant, because you only look at the impedance of the lines. And you can use that to validate your method. If you have now, you have computed a Thevenin impedance, then you can draw this line, the blue thick line. And if your dot still is on that line, you're okay. If it's outside, then you probably have made a wrong guess for the power, the angle here, or that you have a bad measurement. A few words about another method. We come back to showing some result of this. We can also, to a certain degree, use that you know the topology of the grid when you do the voltage stability monitoring. And this is one example about the approach here. This one is also published. I won't go into very detail on it, but just say that if you have a network that you know, for example, this is part of a sub-transmission network or something, you would have some local generation. You would have a number of transformer stations that are basically loads, and you will have connection to the transmission system or the rest of the system. If you now consider all these feeders, whether they are loads or generators, as injection to your system, you can formulate the admittance matrix as you would for any kind of network, and you could rearrange that by some kind of triangularization, so that you apparently have a system that with several Thevenin equivalents then feeding to the load. And then you could use, then you are using the fact that you know the admittances or impedances within this network to compute this impedance. And that you can then use to estimate the voltage stability margin. That is the clue here, without going into all the details on how you do it. It's a manipulation of the admittance matrix, basically. And we also, again, without going into detail, this the application of this, or the strength of this, is that when it's based on the topology, you could always simulate outages or contingencies within this network and come up with different values on your equivalent impedances. So you could then compute Thevenin impedances, let's say in the online case where this grid is intact, and you could simulate what it would be if contingency occurred. So this is then as a sort of a recipe for how you would do that. Essentially, what you would do, you would plot the Thevenin impedance for the case with the highest impedance. So that is sort of illustrated here. That I mean, if you have an intact grid here, it's easy to see that the impedance of this is the parallel of these lines, more or less 100 ohms. This one doesn't count because it's a current injection, so it's and that is also a point here, that if you know that you are at some kind of limit, or if your feeder is controlled by power electronics, for example, the idea of Thevenin impedance falls, because you're into a nonlinear system. You don't know the response to that. So we better consider it as a constant current injection. Then impedance is 50 ohms. But you know that if you lose this line, your impedance will be up to 100 ohms. So you could plot that, and then you would know that in this case, with this load impedance, that you're already in near trouble. So this is just a simulation of what happens if you lose this line. Then the voltage drops and also the power drops. So you're saved exactly, but the margin is very small. But these also have some weaknesses. And you should be aware of the limitations. For example, if you have a capacity banks here, is that it's not always so that the load impedance is equal to the Thevenin impedance under maximum power transfer conditions. It's important to be aware of that. That is documented several places. We can. I thought I would show you before we take a break now. I'll show you some other work that we did. Where is now? Okay. This is actually results from a recent master thesis this spring, who did work in the lab to verify the basically the SZ indicator, but also other indicators. And what is going on here is the following. He has a feeder, 400 volt basically, and what he has all these inductors that he can switch on and off. Maybe series also, and then he has a heater, water heater, that is a load that he can adjust. And here you have a PMU, so measuring voltage and current. And what he is showing when he is doing the simulation is then the voltage as a function of active power when it is using the impedance. And then he is looking into actually comparing three indicators. But you see here, what you see here is the voltage in blue and the current in red. You see that the current vectors are increasing. Mainly it's ohmic loads, right? Current is in phase with the voltage, so it's a resistance. So this is illustrating how these indicators behave. This is the SZ indicator that follows this characteristic slope, right? And this is the presented as voltage as a function of active power. So now you see when this comes to the bottom here, it's fairly close to the maximum power transfer. Now it's really critical when it's on this slope. And then you can, since this is a passive system, it doesn't run into instability, of course, because he controls the load himself. But it can sort of go over the tip. So now he is very close, and he does increase a little bit more, and there he is over the top. And then it goes back then. He can also, what he also did, where he was looking at what is the best sort of indicator from a visualization point of view. Is it delta S over delta Z? Is it like here, delta S over delta Y, where Y, of course, is inverse of Z. Then the instability point is also 0, but it goes from positive to 0. Otherwise, it's more sort of a matter of taste, I would guess. Yeah, this is the last one. And this is the one that is reported by Kostas Vournas, where he I mean, S equals in principle, and Y is G plus J B. And what this indicator is, it's delta P over delta G. That is his version. And there are some minor differences of the performance of those, but we still like ours the best. And this is another example where we switch out some of these to we can make the impedance higher on the grid side. So what happens then? If we could speed it up, it would be better. But you see the same performance again. It's moving on down now, and when it's sort of become critical, what he will do now soon is to do the switching, and then you see it now. It's an indication that something's happening on this. It's kind of critical, but there it happened. And you see it's now on another PV curve, you might say, because this is the post-contingency situation. And you see now it's very close to instability. But then it goes back, it connects this again, so we have higher impedance. No, I mean less impedance. This is a parallel. And then everything, then it follows the original line. And that's the same with the others, but we don't have time. So I think then perhaps it's time for a small break. We have kept for an hour now. And but any questions?
Mainly he discussed some of the research algorithms dedicated for voltage instability point of view, because PMU has one of its potential application to log the voltage instability as well. So thus the algorithms that they discussed that if they say dp by dg, that is monitoring the dp by dg, this is basically is the instability index. Thus to know at what point of we change the load resistance, at what point you are likely to have a voltage instability under collapse. So thus he discussed in his master's thesis, this is what will be the best indicator or the best index to describe the voltage instability. When we have the different load conditions, because our the system you have a random load. So if when you use load, you remove load actually. So when the load changes, in that case the properties of the system changes. In that case you must know what is the best index to say, to indicate to the operator, the voltage instability is 90. That's more important. So that is one of the ones that we have discussed with the customer. And then again, in fact, if I can summarize, we discussed that because in his, he has some of the PMUs, those are actually lab PMUs. He has the PMUs installed in the labs of different universities. One is the NTNU, ATS, Alto, the Ampere University, and the India. So he has the network of those PMUs installed in the lab, and that's the called as smart grid level network of smart grid level. And thus, in the system, that is the entire logic gate system, they are able to know what is the voltage angle and thus what is the frequency in the respective locations of the circuit. So you can know. So being over here, I will say this all he is able to know what is the direction, the frequency of the pulse signal. I can he has shown it for NTNU. This is what we have the application of PMU, and the remote application is monitoring.
Just a quick question. Why do the phasors move? Why are they not standing still?
These are the voltage angles that contact.
No suggestions? They should move continuously. It's just the resolution or the communication delays that makes it, let's say, move in steps. They would move. In reality, they're moving continuously.
It will be at the rate of samples.
Yeah, sure.
There is a delay actually in the signal that we receive here from the team located in the lab. So because of that delay, otherwise it should, because I think you have it at 50 hertz sampling rate.
Yeah. So I mean, why it moves is simply because our reference is 50 hertz. So at any deviation from 50 hertz, these phasors will move, right? As I said yesterday, if the frequency is 49.1 hertz, it would take 10 seconds for them to go one round, one circle. Now it looks like the frequency is quite good now. It's quite stable. as you see. Frequency is now fairly close to 50 hertz. Maybe it's dropping a little now. Yep, okay.